All right. Good morning, everybody. Hey. So let's start with a little bit of a. Let's just look at some of the new things on Moodle. So we've got the. Well, this has been up for about a week. We've got recommended problems in your textbook. So we just got through with chapter 15 with the hypothesis testing. So this just gives you some problems that you could try. And then we'll do 16 and chapter 17 as well. Get back here. Okay, so now we've got inference summary sheet. I think I got a question about that. So you should have gotten this in your lab last week. You may have not. Maybe you'll get this Thursday. I know like one lab was TA forgot to pass it out, but that's fine. Yeah, it's up here. This is what the summary sheet is. And again, you can use. We'll pass this out with the final exam, so you'll be able to use all of these. You'll get a fresh copy. So yeah. All right, another thing. We've got how to calculate your grade. So I updated this so that it's with what the syllabus says. So we've got 3 exams. Got worksheet average, weight is 10%, Handon 11%, MyStatLab 10%. So what you would do is you'd use this that formula right there to find your score. So if you got like a 90 on exam 1, an 80 on exam 2, you'd put that in to this spot right here. So 90, 80, and then you look at your average on Moodle for the worksheet, homework, and your online. So MyStatLab, MSL. And then you can do one of 2 things. You can either make a guess for what you think you'll get on exam 3. Say, oh, I think I'll get a 95. So then you put that in there, and then you just see what your final score, your grade will be for the class. Or you can say, I want to get at least a 67.5 to get a C minus. So I put an X in for exam 3, so it's an unknown, and set this all equal to 67.5 if you just want to make that C minus. Yeah, C minus. Okay. All right, any questions with how to do this? So yeah, this is up on Moodle. You can look at this, and yeah. Anything else? Okay, so we've got the last homework in this class is homework 9. And I have that's already up on Moodle. You'll be able to get access to it after you turn in homework 8. And then we'll have 2 more worksheets, worksheets 11 and 12. So there's 2 labs left. So this lab, this Thursday, and then the lab after you come back from Thanksgiving break. That'll be your last lab. So last week before finals. All right. Yeah, videos. Yeah, I'll do practice exams again. I'll try to get those up on after Thanksgiving, on the week back. So you'll have time to look at them. All right. So let's look at the announcements for today. So we've got Handon homework 8 is due tomorrow. And then we've got the chapter 15 for StatLab, the online homework, is due on next Monday. And then Thanksgiving break is next Wednesday and Friday, so no lab next week. It'll be Turkey Day. And then yeah, exam 3. It's a final. That's on Thursday of the finals week, December 12th, 8 to 10 a.m. here. All right. Any questions with that? Do you feel like you kind of know what's going on? That's good. All right, so let's get into the course pack here. All right, so we're getting into chapter 16. So this is pretty much, it's like that chapter where we had regression wisdom. So it's just a couple, some important things to know about doing tests and about intervals. And so we want to make the connection between doing tests and then also supplementing that with a confidence interval as well. And what that will tell us is it will tell us the like how far away you might be from using your data. So you can get so what I'm trying to say is you can get two hypotheses. And you can determine that you like the alternative hypothesis. There's evidence for the alternative hypothesis. But then the difference is so small, it isn't really practical in real life. It doesn't really matter that much. So that comes into play when you have like a large sample size. So you'd have a very, you could tell just a very small difference. But maybe in your context, yeah, that just doesn't really matter. So. Yeah, and that's what this first bullet is. So how big is the difference? And then also, you can't rule out other possible parameter values. So maybe it could be, instead of greater, it could be less, or maybe it could just be a little bit off, like just so little off that you wouldn't be able to tell unless you had a really, really big sample size. All right, so we need a confidence interval. That's what we need in order to tell how big of a difference we have. So let's consider the steel beam example again. So this is on page 226 of the notes from chapter 15. So we've got the two hypotheses, H0 and HA, where H0 is that the proportion of defective of steel beams was 0.12, or the other hypothesis is that there's less. So the other process is saying that there's a lower defective a rate there. All right, so then we've got a p hat, 13 out of 150 of 0.08667. And then since we're doing the confidence interval, we use the p hat to make our confidence interval. So we're not using p naught here. So yeah, so this is 0.08667. It's not 0.88. And there could be a bigger difference there, and that would mean that your confidence interval would be even farther off if you did the wrong thing. So let me write that down. So so standard error is not equal to square root of 0.12 times 0.88 all over 150. All right. Okay, so we have our confidence interval. It's from 0.04 to 0.132. Yeah, maybe we could just go over this again, just so you feel confident with your confidence intervals. Yeah, and let's look at the well, when you're faced with a problem like this, so we're looking at the top now. So we've got all the confidence intervals here. So we're picking one of these four. And then we know that this is it's a proportion, so it's going to be one of the top two. And then we're just using a single proportion. So there's not a P1 and a P2, there's just a P. And so the calculator function is a 1 prop z-int. And then the formula is p hat plus or minus z star times the square root. And here, p hat times q hat over n. And then z star, so this is a 95% confidence level. So z star is down here. So right there, 1.96. And then also you can check your necessary conditions to use the central limit theorem. There's the 3 conditions: SRS, 10% condition, 10 successes and failures are expected. All right. So you can see this would be a pretty useful sheet right here to use. So yeah, I would start just like we did. I would start from the first column, and then I'd work my way to the right as far as when you're using this this table here. All right, so here we want to be able to say whether or not this is consistent. So we've got, wow, everything looks purple now. So we see if 0.12 is within this confidence interval or not. And it is within. So that our conclusion was that that there was suggestive evidence that the new method was better than the old. And here, it's consistent. Right there. All right, any questions with that? Okay, next page. Yeah, I fully expect to get through this entire course pack this semester, so I'm kind of excited about that. Yeah, we may even have a day for review on the Friday of the last week of class here. All right, so we've got the confidence interval also includes values that are smaller than 0.12. So P could be 0.12, but we also think that it could be much smaller. So that's just the suggestive part of things. So 0.12 was in the confidence interval, but then there were also a lot more smaller values that were less than 0.12 in the confidence interval. And then maybe they would the manufacturer would only want to switch the process over if they're getting a 0.05 defective rate to make it worth switching over. And then our results would be inconclusive from this. All right. Okay, so how should you make a conclusion based on a p-value? All right, so again, we don't say one hypothesis or the other is correct or incorrect. It's just evidence for one or the other, and that depends on what the p-value is. So this is a review. So this is exactly what we've learned. I forget what page it was on. It was on a few pages back. So this is one way. This is the subjective view. But then another way is it's the decision-making view. Yeah, but let's look at another graphic first here. So this is from, it's based on Ramsey and Schaefer. And this is just, it's indicating what p-values would be convincing, have moderate evidence, mild evidence, suggestive evidence, or no evidence. So you can see that's a little more, a lot more down here. And then it gets a little more rarefied as you go up. All right. So then, as an example, just to hammer this home, I guess, is this back to the Hopkins forest example, page 235. We had a p-value of 0.0051. And then we could say that it was strong evidence because it's less than 0.01. Strong evidence that the proportion of acid rain damaged trees in the Hopkins forest is greater than 0.15. And here's something new right there, something you may not know, is that even though the test was two-sided, in your conclusion, it's totally okay to give a direction, say that. So here we said that it's greater than 0.15, and that's based off of what the sample was. So the sample was, I do believe it was greater than 0.5, greater than 0.15, and so we would tend to think that the proportion would be greater than 0.15 because of that sample. Does that make sense? So so you could also say just different is different than 0.15. And that's what you started off with. And that would be correct as well. All right, so let's get to something new here. So we've got a decision-making view. This is the other way to go about it. And some people really like this. You know, I'm more of a fan of the subjective view because you can make your own judgment on that. You don't have to be so rigid or like, yeah, you can you can make your own judgment on that. And yeah, it's a little more flexible. I like that. All right. So this is if you want to make a firm decision whether the null hypothesis is true or not. And then, so at the start, so at the outset, so when you're just deciding to do this test, you decide this alpha level. So you say, I'm not going to choose HA unless I get a p-value that's less than alpha, less than this number. So alpha is called the alpha level or the significance level. This is the Greek letter for alpha. Kind of looks like an A. But then, as always with the Greek letters, there's an extra tail. So, yeah. Okay, so and then when you're talking about this, you just say that you could reject the null hypothesis at the 0.05 level of significance. Or then you could say that you failed to reject the null hypothesis at the 0.01 level of significance. Those are two examples. So you should mention the p-value, and here you should mention the alpha level as well, just so you're clear with what the cutoff point was. Another way of saying this is that you could say that the result was statistically significant at some level. And of course, you can say percents instead of proportion if you want, if you feel like it. So yeah, this alpha level is chosen by the researcher. Yeah, you want to set this in advance because you could choose any alpha level to draw any conclusion you want. Yeah, set in advance. So yeah, if you look at your p-value first, then you could choose an alpha that was just like a little bit higher than the p-value. So if you're choosing an alpha level of 0.0659, it might be a little suspicious if your p-value was 0.658 or 0.0658. Yeah. And I guess there's really, I don't know how you would check, how you would know whether the researcher did this or not, set it in advance. But it should be so that you don't affect your decisions in that way. Yeah, because you as a researcher, you don't want to be you want to try to be you don't want to be so set in your conclusion before you gather your data. So you want to gather your data and then make a conclusion. You don't want to have a conclusion and try to back it up with finding data, doing experiments, if that makes sense. So yeah, that's kind of a basics of a scientific method right there. All right. Okay, so here back at the Hopkins forest example, the p-value was 0.0051. And then we've got three alpha levels here, 0.05, 0.01, 0.001. And we try to decide whether or not to, what our decision should be. All right, so with this one, we reject the hypothesis. That 15% of trees are damaged by acid rain at the alpha equals 0.05 level. All right, so 0.0051 is less than 0.05. And that's why we reject the null hypothesis. All right, and then same thing for the second one. 0.0051 is less than 0.01. So I don't, yeah, I'm not going to write that again. Same decision at the alpha equals 0.01 level. But then this third one, this third alpha, is actually smaller than 0.005, 0.0051. So 0.001 is less than 0.0051. So you would say that you failed to reject the hypothesis. So you failed to reject the hypothesis that 15% of trees are damaged by acid rain at the alpha equals 0.001 level. All right. So this is how the decision-making process works, is depending on what alpha you have and what p-value you have, determines what decision you make. So. Okay, so using a fixed alpha level to make a decision is ingrained, so it's used all the time by people in many fields. But then some statisticians don't like it for several reasons. One of the reasons being that there is really no sharp border between significance and insignificance. So it's a little bit of a gray area. Just in all reality, two people might make a different decision if it's kind of on the borderline. All right. And then there's just stronger and stronger evidence against H naught. And then also it's more informative to report the actual p-value as opposed to giving these alpha levels, because the alpha levels give you a possible range of values that the p-value could be. But it's nice to actually just look at the p-value. So like if you had alpha of equals to 0.05, the p-value could be 0.03 or it could be 0.00003. And those mean completely different things. So completely different levels of evidence, or how much evidence you have. Okay, so also when you make decisions, you should not solely base them just on what this p-value is. You should use some other considerations. So like here's a good one. Is it safe? So if your hypothesis tells you to jump off a cliff, you should not do that hypothesis. So that's a pretty good concern. Is it ethical? All right. So is it? Yeah. Is it not just safe, but is it the right thing to do? So this comes maybe into a lot of like animal testing. There could be safe things for humans, but then it's not really ethical to do any experiment you'd like on animals. There are lines, and then there's privacy issues, I guess. Yeah, that I don't know how often that would come up in research, but it could come up. So, privacy issues. Is it good for the environment? Let's not forget about that. So yeah, the real world is very complex, and there's a lot of things to consider, and so you should be trying to think of a lot of different things when you make your decisions, not just one p-value. Although it can be very, very, very helpful if the two choices are very, very similar. All right. Okay, so now we're looking at statistical significance versus practical significance. So the difference here is that, yeah, does it matter is pretty much what this section is about. All right, so let's say we have company is advertising. So they're advertising on a local radio station. And they want to increase their product recognition. All right, so they're assuming that 20% of their community already recognizes their product. So right now we should know whether this is a proportion or mean problem. Anybody say? Which is it? Should it be, is this equal to a mu or equal to a p? I should cover up the, yeah, you can just look down the page, but yeah, right. Yeah, very good. All right, so what they do is they sample these residents, and they want to see if they recognize their product, their company's product. So they want to see if there's an improvement in their name recognition. All right, so now we have to compute the p-value in each of the following sample cases. So they could pick a small sample or a large sample, and the p-value is affected by that. All right, so we could survey 100 people and then have 21 recognize them. Could survey 1,000, and we have the same p-hat, but just a larger sample size. And then we could survey 10,000 people and have the same p-hat as well. But then let's just go through how to find the p-value again. As always, you want to sketch a graph, sketch a distribution of this. It looks like this. We're assuming that 0.2 is the center here. Using the central limit theorem, we know that p hat is approximately normal, the center of 0.2, and a standard deviation of 0.2 times 0.8 all over 100. Oh, sorry about that. There you go. All right. And that is 0.04. Okay. So then this would be 0.24, 0.28, 0.32, 0.16, 0.12, 0.08. And then this is a p-hat with the sample size of 100. All right. Okay, so we have 0.21 is our sample proportion. And that would be right about here. And then which way should we shade, to the right or to the left? Yeah, to the right. We got that from the greater than sign in the alternative hypothesis. So on the previous page. All right, so now we have a p-value is equal to normal CDF and then we go from 0.21 and we go to the right. So those are our first two entries. 0.21, we go to the right. And then we have a mean of 0.2 and a standard deviation of 0.04. All right. Okay, so then for this other one, we have a new picture. So, and we know that the central limit theorem tells us that p hat is approximately normal, center of 0.2, but then now we've got a standard deviation, a square root of 0.2 times 0.8 over 1,000. So there's the difference right there. 1,000. Right there. So there'll be a smaller standard deviation. It'll be 0.0126. And so if you, yeah, let's find what these tick marks are. So we've got 0.21, 0.23-ish, 0.24. Point 0.19, 0.17, 0.16. Right there. All right, and this is a p hat, sampling distribution of p hats. N equals 1,000. There. And so now 0.21 looks like it's a little further up here. And we have a smaller region of that distribution is shaded in. That's just because the variability decreased, and so everything is just closer to the mean. All right, so we've got a p-value equals normal CDF. And then only one thing will change here. It'll just be the standard deviation. So we have this. We have the same p hat. We're going to the right still. We've got the same mean, but then a different standard deviation because of that sample size. And that should give you 0.214. All right, let's just do this last one real quick. So now the central limit theorem tells us this. So we have a sample size of 10,000 now. And that will give us a standard deviation of 0.004. All right. And let's find our tick marks. So we've got 0.204, 0.208, 0.212, 204, 0.208, 0.212, 0.196, 0.192, 0.188. And this is a p-hat with n equals 10,000. All right. So yeah, sample size does matter. It's changing our pictures here. And now we just got a little sliver up here that is shaded in. Well, I guess, yeah, it looks more like a wedge, I guess, a little wedge that's shaded in, little region. It's not a sliver. All right, so we've got a p-value, normal CDF, and again, we shrink down our standard deviation. 0.004. Type that in. Should get a 0.006. All right, so this is finally statistically significant. There's difference. So in the first two, we had p-values that were not very convincing. P-values of 0.401 and 0.214, those are pretty high and not very convincing. But then suddenly we've got a convincing p-value. So it is statistically significant. It's great. But whether or not it's actually practical, like of practical importance, is something else. So just a 1% increase isn't really that much. So that's what this bullet is saying. And then in a more succinct manner, look at the second bullet. So that's saying that statistical significance is not necessarily the same as practical significance. Oh, yeah, we could say no there. We wanted to. Okay, so yeah, let's do a little bit of an example now with what would happen if we changed. Let's say that you're given the p-value for let's look at a couple different tests here. So let's say we had an H naught p equals 0.2, HA p was less than 0.2. And then here, so this is case one. And then let's say you had p equals 0.2, but instead you had p not equal to 0.2. So if you, let's say you had a p-value, say you had a p-value of 0.87 in case one, then what would the p-value in case 2b. All right. So with these set of hypotheses over here, it's best to draw a picture here. So we're shading to the left, and we'll have an area of about 0.87. So that means that our p hat will probably be somewhere around here, and we're shading to the left, like so. And of course, you know, we can't really fill in too many details because we don't even know like the sample size here or anything. But let's assume the sample sizes are the same. So they have the same sample sizes. Everything's the same. It's just that one has a less than, and the other one is not equals. All right. So here's the issue. So you don't want to just multiply by 2, or else you end up with a number. So don't just multiply by 2. Because then the p-value is equal to 2 times 0.87, which is 1.74, which makes no sense. All right, so we don't want to get probabilities that are greater than 1. It has to be between 0 and 1. But instead, everything's the same here. So we would have the same p hat from our data. But then instead we have 2 tails like this and like this. That's what the not equals sign means, is that we've got the 2-sided test. All right. And then define what this area is. It's just 1 minus. So we take 2 times 1 minus 0.87 from looking at our picture. So everything else besides this is 0.13. That's the same as this area. And then we take 2 times that because we have 2 tails. 2 times 0.13 is 0.26. So case 2 has a p-value equal to 0.26. Right there. All right, I think, yeah, we can just end right there. We'll finish this chapter up on Friday. So have a good day, guys.